Welcome to this explainer. Look, if you're gearing up for a technical interview and your goal is to walk out with an actual offer to be a software engineer, you are in the exact right place. Today, we're doing a deep dive into manipulating arrays. And we aren't just going to sit here and write code. No, we're going to learn how to actually think like a top-tier algorithmic problem solver.
All right, here's our roadmap for today. We're going to start with the golden interview strategy, dive into the art of array rotation, master the two-pointer technique, conquer sorted arrays, and wrap it all up with the ultimate complexity check. Let's get right into it.
So starting off with Section 1, the golden interview strategy. And the subtitle here really says it all, showing your work. You know, getting the right code up on the whiteboard, that's actually just part of the battle. It's really about the communication journey. So, the absolutely crucial point here is do not jump to the optimal solution directly. You've got to show your thought process. When you're in that interview seat, you're the one driving. Even if you look at the problem and instantly know the mathematical magic trick to solve it in big O of one space, hold back. Seriously. The interviewer wants to see how your brain formulates a basic plan, finds the holes in it, and iterates toward perfection.
I like to think of every single problem as this escalating three-round match. Round 1, brute force. Just get the easiest, most obvious working solution on the board before the nerves kick in. Think, using a temporary array to hold elements. Then round 2 is your better solution. You optimize it slightly. Maybe you save some time, but you're probably still using extra space. Then we hit round 3, optimal. This is where you lock in the absolute best time and space complexity, usually doing the work in place right before you inevitably run out of whiteboard space. Taking them step by step like this leaves a massive positive impact.
Moving right along to Section 2, the art of array rotation. We're talking about shifting elements effectively. Let's see how that three-round strategy actually applies to our first challenge. Imagine a standard array of numbers. Left rotating by d places just means we're shifting all the elements in that array to the left. But what happens to the poor numbers that fall off the front edge? Well, they don't just disappear, they wrap around and are moved directly to the back of the line. So, if you left rotate by 2, the first 2 numbers jump to the very end, and everything else simply slides forward to fill the gap.
Now here is a mathematical shortcut that interviewers absolutely love to test you on. What if the array size is 7, and they ask you to left rotate by 15 places? Brute force would literally shift elements 15 times one by one. But think about it. If you rotate an array of 7 elements by 7 places, it ends up in the exact same original order. The whole thing just looped. So any multiple of the array's size is just a wasted rotation. We can simply use the modulo operator here. 15 modulo 7 leaves a remainder of 1, which means rotating by 15 is literally identical to rotating by 1. Pulling out that little trick instantly proves you understand efficiency.
But how do we physically do this in code without creating a whole new copy of the array and just wasting memory? Well, here's the brilliant 3-step reversal trick. Step 1. Just reverse the order of the first d elements. Step 2. Reverse the order of the remaining elements. And finally, Step 3. Reverse the entire array. Bam! Like magic, the exact rotation is complete. You don't need any temporary arrays, which means our extra space complexity drops all the way down to big O of 1.
All right, Section 3, the two-pointer technique, or as I like to call it, dancing across the array.
So we just saw how to avoid extra memory using array reversal. Now let's dive into the ultimate algorithmic pattern for minimizing space complexity. Here's a super classic interview question for you. You're given an array of integers, and it's mixed with a bunch of zeros. How do we move all those zeros to the end of the array, keeping the other numbers in their original order without using any extra space? Take a quick second to think about how you'd physically move them.
Okay, so the brute force way is easy, right? But it's super memory heavy. You just iterate through, grab all the non-zeros, chuck them in a fresh temporary array, and then fill up the rest of the slots with zeros. Easy. But that takes big O of n extra space. The optimal way? We use 2 pointers. Let's call them I and j. Pointer j goes hunting for the first 0 and just camps out there. Meanwhile, pointer I keeps marching forward looking for a non-zero number. The second I finds one, it immediately swaps its value with the 0 sitting back at j. Then j steps forward to the very next 0. It's this elegant in-place little dance that pushes all the zeros to the back, all while traversing the array just a single time.
Which brings us to Section 4, conquering sorted arrays. It's time to start juggling multiple data streams.
Up until now, we've only been dealing with a single array.
So let's escalate things to two arrays that are already sorted. There are two classic operations you've got to know here. The union is taking everything from both arrays and combining them, but crucially, without keeping any duplicate numbers. The intersection, on the other hand, is strict. It only extracts the specific elements that are present in both arrays. They sound kind of similar, but mechanically, the algorithms to solve them flow quite differently.
Let's take a look at the brute force method for finding a union. You might be thinking, oh, I'll just dump every number from both arrays into a set data structure. Sets automatically delete duplicates, and yeah, sure, that works. But look at the limitations. A set data structure typically inflates your time complexity logarithmically as you insert items. And worse, by the end of it, your space complexity blows up to big O of n1 plus n2, simply because you're storing all those unique elements externally. Trust me, the interviewer's going to push back on that kind of space usage.
And the exact same issue happens with intersection. The brute force way uses a nested loop. You pick one number and you scan the entire second array looking for a match, usually keeping a visited array to make sure you don't double count. And this brilliantly illustrates why paying close attention to the prompt is so vital. The prompt told us the arrays are sorted. Because they're sorted, we can use the optimal two-pointer method instead. We just start a pointer at the beginning of each array and move them based entirely on which number is smaller.
Here's exactly how that two-pointer intersection logic plays out. You compare the elements sitting at your two pointers. Step 1, if the element in array A is smaller, it's literally impossible to find a match for it later in array B, because array B is sorted and only going to get bigger. So you just move pointer A forward. Step 2, if array B's element is smaller, same logic, you move pointer B forward. Step 3, if they match perfectly, boom, you found an intersection. You add that number to your answer, and you increment both pointers to go look for the next pair. It is incredibly fast and runs in strictly linear time.
And finally, Section 5, the ultimate complexity check. Think of this as your interview cheat sheet.
Let's lock in everything we've been building up today. I highly recommend you screenshot this cheat sheet right now. Seriously, when you walk into your interview, this table needs to be burned into your memory. Look at left rotate, moving zeros, even a basic linear search. The optimal time is big O of n, meaning we just iterate through the array proportionally to its size. But pay special attention to that third column. For every single one of these algorithms, the extra space required is big O of 1. We aren't building massive new structures, we are manipulating the data in place. Now, even for union and intersection, while we might need space to return the final answer, the algorithm itself only utilizes big O of 1 extra space. Just always be sure to clarify that subtle difference with your interviewer so they know you get it.
Well, we have covered massive ground today and hopefully given you the mental models to totally dominate array problems. But I want to leave you with one final provocative thought. We learned how to completely master the left rotation of an array using that really elegant three-step reversal trick. But what if the interviewer throws a curveball? How would you write the optimal algorithm to right rotate the array by d places? I challenge you to grab a piece of paper right now and try to reverse engineer the logic we just learned. Keep practicing, keep optimizing that thought process, and I'll see you in the next explainer.